Right, so we move on, and I would like to introduce Rodrigo De Negri, our next speaker. He's a researcher at the Laboratoire Magma des Volcans in the University of Clermont-Auvergne in France, and today he'll be talking about the volcanic information system and the use of long-range infrasound monitoring at volcanic eruptions. Floor is yours.
Okay. Can you see it? I don't know. I can see it there, but not there. Okay. So thank you, Lorraine, also for introducing infrasound. Very fascinating topic. I want to acknowledge all the scientists. I don't know why it's not there yet. Okay, thank you. That are part of this project. It's not just me. It's a community-based project based by Joe Inquirer. And today I'm going to try to summarize this work in these four parts. A very short introduction of volcanoes at infrasound, and then we'll spend most of the time in volcanic information system. That is what I'm going to mainly, the main point of this presentation, and mention a couple of challenges, what's coming and what has been done very recently, actually. So, well, infrasound basically is acoustic waves below 20 hertz. We cannot hear them. And volcanoes, in particular, produce infrasound usually around 1 hertz. It's more or less the range. But volcanoes also produce many other signals too, as here I'm showing you. But when there is an eruption that has an ash column that is sustained, there is a bunch of infrasound produced. The signal has specific characteristics that we are going to exploit for the volcanic information system. But we are not alone. There is many other natural and anthropogenic phenomena that produce infrasound as well. This is one of the main challenges of trying to extract volcanic infrasound from other sources. As mentioned, microbariums is a big source of infrasound. For me, that's kind of noise. Isn't that how it goes? But when infrasound and volcanoes started to be studied, I think it was from the Krakatoa eruption in 1883. This eruption was so big that was actually seen by meteorological stations in the globe. On the top right corner, there's a globe with black squares that show the positions of these meteorological stations, and the volcano is in a red triangle. And they could be seen at about 4 times passing the wave with non-specialized equipment. So now imagine that the same happens in 2022, that is basically hung eruption. This was a phenomenon to study from this perspective. There's the IMS now. There are many other technologies that collaborated to study this eruption and characterize it before, during, and after. On the left, you can see how satellite, for example, images are overimposed on the myriad of stations and how each kind of technology, like hydroacoustic or seismic, starts detecting the activity, and then infrasound takes the main lead, and then so on. There are others that come after. Anyways, on the right, you see 4 just IMS stations. You could see about 16 passes of the wave now, not just 4, which is quite amazing to see, an incredible opportunity to study volcanoes and infrasound. Now, this is all thanks to the IMS. I want just to mention this here. Infrasound is just a sub-part of it, but the multi-technology component of it is very important for any monitoring system, really. And when you look at the IMS infrasound array and look at the volcano positions, you see naturally you come with the idea of why don't we use infrasound to monitor the volcanoes in 24/7 way, right? And that's it. That's a volcanic information system. The idea is to do an infrasound-based methodology for remote detection. Here, remote means beyond 250 kilometers nominally. You don't need to be in there. The infrastructure is already working, and let's use it. And why we want to do this is because mainly, well, not mainly, but one very big risk of volcanic eruptions that are going to happen yearly, that are like the volcanic eruptions with a volcanic explosive index 3 or bigger, is that they produce a lot of ash. Encounters by aviation are very, very risky, and you want to avoid them as soon as you can to know where is the ash plume, when it was generated. It requires a 24/7 monitoring system, and we think infrasound can be integrated in the current systems that are satellite-based. What is this is basically a series of steps to extract the volcanic signal from all the others and characterize an eruption when it happens. So I'm going to use the example of Huye-Gordon-Kauye, that is an eruption that happened in my country in 2011 that produced a big ash plume that was sustained. This is a VI4, it's a little bigger than the eruptions at VI3, and it produces a sustained plume about 10 to 12 kilometer heights, affected large areas, especially in the Argentinian side. So if we look at the detections here, and at this moment to mention, I'm using the open access database from the IMS data. You can access this data actually. It's a reprocessing. If you're curious about it, it's great for scientific research. So here on the top right, I'm showing these three subplots for each one of the stations, I02 in Argentina, I08 in Bolivia, and I41 in Paraguay. I'm sorting the detections by time in the x-axis in the whole year 2011, and the color is for the frequency. Lower frequency is the blue, higher is yellow. So you see there is a mix of colors there, and on each one of the subplots on the y-axis you see the azimuth with respect to the target volcano. So 0 azimuth means towards the volcano exactly you're observing here. What the main problem you see immediately is that there's too many detections, right? We call this clutter. So this is the first filter, looking at the specific direction of the volcano. Now, first we look into, in a little bit shorter time window, in a week is more clear than, at least for these two I02 station and I41, there are detections hitting more or less at 0 degrees, that means towards the volcano, in the time this eruption happened. I'm talking here the stations that are 1,500 to 2,700 kilometers away, so it's quite amazing to see this. Now, if you zoom in into the azimuth, you see that if you were thinking an algorithm to look at the direction of the volcano and selecting those detections, you would fail here. This is why I'm using this case, because the detections are deviated from where they should be. Okay, so there is something we have to take care here first, and that is that there are winds in the stratosphere that deviate these detections and cause an apparent back azimuth that is not the one that you expect. And this time of the year in June, you had winds towards the east that produce a deviation that is similar to this cartoon here. Basically, there's an offset that pushes the apparent source to the east. If you pre-calculate that, because that can be pre-calculated, and use that instead, you see in now the red line is a corrected, quote-unquote, back azimuth that I expect to have, and those back azimuths correspond more or less to the detections where they are. So now we are able to actually grab them, right? But there are other problems here, of course, there are many, but one of them is that there are local sources. So I was hoping to have a pointer, but if you look at the bottom plot at I41, in March, just like in between March and May, there's a group of detections that fall in the back azimuth that you expect that are not the main group of detections that correspond to the eruption. If you were looking at eruptions, you may think that there's an eruption, and that's a false positive, and that's very bad for a monitoring system, of course. You need to remove those, and that's what we're going to do now. So we're going to take the amplitudes of those detections and back project to 1 kilometer from the source and look at the theoretical amplitude they should have. If that amplitude is bigger than 500 pascals, we will not consider them because eruptions don't produce as high as amplitudes at 1 kilometer from the source, most of them. Tonga eruption may have, but most of them don't. So if you apply this filter now, those detections are removed mostly, and you will avoid a false positive, right? Next step is, well, we look now in time, and we zoom back again in some days, and it's much more clear which detections we're selecting. And the final step is to look into the persistency of the signals and calculate the IP parameter, that is a detector, basically, that was developed around Etna volcano, first locally and then for remote distances. So you just consider detections that are persistent enough in your time window to correspond to a volcanic case. Volcanoes are transient events, and also the dispersion in the atmosphere elongates the duration of the signal, which also means you have a more persistent signal, basically, at your station. If you include these two and calculate the IP values and combine them, you see each one of the stations is collaborating to find an IP value above 100, and you can reconstruct the eruption at thousands of kilometers away from the actual volcano. In the bottom plot, in red blocks, you see the different times of the eruption that are automatically found by this algorithm. You can tabulate this, and very nicely you see You found them in June. Now, there is a thing that I haven't told you. There's a time delay added because the sound is low. Per 1,000 kilometers is 1 hour. So 1,500 kilometers, 1 hour and a half. You will ask yourself, is this useful? And we can say that resoundingly yes. Here you are comparing in blue lines and red lines the IP or the vis monitoring detections for different eruptions. And in a green line, ash plume detection by satellite. In red lines, the official ash notifications to aviation. For several cases, you can actually find these infrasound-based detections before or corresponding to what you say satellite, and many times before the official monitoring notifications. So we think there's a space here to collaborate with satellite and infrasound, especially to improve and make more robust 24/7 monitoring systems. We have tackled these two challenges, the first two, atmospheric and clutter. Now, just a second to talk about data availability. Currently, it's not possible to access 24/7 IMS data, but we are testing this on the open access data. We hope in the future we can do something to have a more, at least near real-time access to it. But also this can be complemented with local arrays. We hope to do that too, not just IMS infrasound stations. About the challenges, the natural challenges of the volcanic activity itself, infrasound is it just tells you the scene eruptive period, and you should always combine the technologies that you have to characterize it better as that study. We have already done a workshop in Florence. There will be an open source project that we up soon in that GitHub repository there. It's not yet there, but it will be. We are working on near real-time tests to high reliability, and we want to have a web interface for people to console this system. So if you are interested, if you have a group of researchers that want to work in this, you have an an infrasound station, that you have locally, and you want to use the data to look at volcanoes, please contact me. There's my email or my GitHub account, and thank you very much for the opportunity.
Thank you very much, Rodrigo. Let's see how many questions have we got for him. Let me just break the ice a bit, and just for thinking from the AMS perspective, the network, we are very proud of the coverage that we have with our network. From your perspective, you use our data purely for monitoring volcanic eruptions. Where do you see in the world places where you would like to have more stations? Hypothetical, of course.
Yeah, I think there was a study, I don't know if it was Taisne, but I think there was one paper that said that near Indonesia, one station would benefit a lot the community, considering how earthquake prone is the area, or tsunami genic. From my perspective, from South America, I think more stations in the continent would be better. We have all our stations aligned along the Cordillera, which is good for our north-south resolution, but not east-west, which could help a lot. I think it's not a question that I can answer myself. I think, but in my opinion, maybe it would be very beneficial to have a station towards the east of South America. Mm. Yeah, it's a good question. It's a question for a study.
Thank you.
Yeah.
Have you got any other questions for Rodrigo? There in the back, please. Get it near the microphone, please.
Hello, Tom Hoffman, CTPTO. I find it fascinating. That presentation was very nice. Actually, the first time I have seen application directly where you say, okay, now take infrasound and get rid of all the problems, and then you find some really useful civil application for it. So this is wonderful.
Thank you.
But I think the biggest hurdle for my thinking always was the time delay, because those waves are very slow.
Yes.
And can you say a word about this? Because you had this chart and say you're faster than others. So is it fast enough, or do we have to have more stations in the network to really use it?
Yeah, I mean, I'm very aware that each one of the infrasound stations is extremely expensive to put there and maintain. So in an ideal world, I would have a much more dense array system, but as I show you in the last plot, there was a RISE experiment in Europe that brought together national infrasound arrays for a period of time that made our network array in Europe be much, much better than before, right? So what I think could help a lot is to, I don't know, make this technology more, make more scientists aware this technology could be used in this way. This is something that I'm trying to do now. So they are motivated to put together infrasound arrays in different parts of the world for different purposes. You can use it not just for volcanoes, right? And in terms of the time delay, as I mentioned, I think my biggest problem here was more like the time delay, the 12 minutes of time that I had to present all of this. Actually, that's a very good point, and I think to make other people know that the times of the official notifications to aviation have a big delay that eats out, in many cases, the time delay that an infrasound wave can have. So during the time you're analyzing a volcanic event, you are waiting a lot of time and you're gathering information. So during that time, infrasound can come and tell you also, corroborate there's an eruption or not, and can tell you the amplitude and can tell you maybe even a plume height estimate. So the point that I'm trying to make is that each technology has problems and good things, and they should be more integrated. And infrasound, it's ready to be integrated in a different monitoring system as well. It's not the solver of all problems now. Nominally, hopefully you will have stations at 300 kilometers away from the volcano that you are trying to target. That's perfect, and that worked for La Soufrière in 2021, and that's one of the plots I showed there. It was very good, a very good monitoring distance, right? But if you are within 1,000 kilometers, you still have a lot of time in this bigger picture of the processing workflow of trying to generate a NASH notification, right? So I don't think it's that big a problem as it seems to be, basically. Yes.
No other questions on the floor? Quick one.
I've got it, yes, if you can answer really briefly. What matters to aviation partly is the amount of ash and the size of the particles. Are the types of studies you do able to offer any information about that?
What infrasound can do is to tell you there is an eruption happening, the estimated amplitude, so probably you can link that to the kind of activity that you have, and also you could have a first estimate of a plume height, but looking at the particle size is part of a different technology, basically. So how I think about this is that infrasound can tell you very early where is the ash cloud and more or less the height to use basically propagation models in the atmosphere to understand where the ash cloud is going and to prevent accidents down the ash plume. The part of the particle size should come after, right? It could be triggered by this kind of thing, you know. Yeah.
Well, thank you very much, Rodrigo.
Yes, thank you.